Okay, this is a different topic than I've announced. I have exchanged my talk of today about particle waves with Wolf Beer on Wednesday afternoon. And this is now the other talk which I wanted to give here about to present a particle model which explains relativity and quantum-related phenomena in a classical way. That means I try to explain and will explain particles to a high extent without any reference to quantum mechanics. Okay, I'm not inhibiting this, somebody. Okay. I first have a little textbook, excerpt here from a German textbook about particle physics. It says even though the spin and the magnetic moment are properties which in case of the electron can be observed addressed, these properties result from a theoretical treatment only by correct relativistic description. There is some introduction, and then it says here, and then I find it important, it is not surprising therefore that spin and magnetic moment defy any classical vivid interpretation. And that is something where I object strongly. I say we have the chance for a physical understanding, and in contrast what Peter Rollins has said, I believe that we do not need so much abstraction as we do now. We can understand it in a vivid way, in an imaginative way, and that is what I want to show you here. So, the arguments, okay, which particles are affected by this? That are electrons, for instance, the electrons, the gluons, and quarks, and with some restrictions, it also applies, these explanations also apply to photons. Okay, we know that particles have some properties, and this, we can make conclusions out of these properties. For instance, what is going on here? Yeah. We know that most particles have a spin, and that means, classically, there must be an extension, and there must be first a circular motion, otherwise an extension, otherwise there cannot be an angular momentum. And if there is an electric charge, then we have a magnetic moment, and also a magnetic moment is not possible without a circular motion and an extension. Then, the momentum law tells us that such a particle has to have two subparticles, because one single particle can never oscillate, it can never circulate, because that would mean a violation of the momentum law, conservation of momentum. And then we know we have relativistic dilation, and the relativistic dilation can be deduced from the fact that there is a circular speed of that the motion on a circuit goes on with the speed of light. That was already found by Joseph Larmor and Lorentz in the beginning of relativity to explain dilation. It's not new. And if the circular speed of these subparticles are speed of light, then the subparticles cannot have any mass, because that would violate relativity, and that means by any interpretation of relativity would be violated if this would be not the case. So here we have a set of assumptions which have to be, set of properties which have to be fulfilled, so that a particle does not violate known physical laws. And if we take this together and build a particle model, then we end up with such a model. That means there are two subparticles which have no mass and orbit each other at the speed of light. Here I have the arguments again. I've shown them separately. I've given this a name. It's a basic particle model. These subparticles have the name, my model, basic particles. And I assume that this model is true for any particles. It is true for electrons. It is true for quarks. And with some restrictions, it is also true for photons. And there is no conflict with experiments, which I will now show at once. So, the normal argument is this is in conflict with experiments. But that is not true. I've discussed it with people who have made such experiments. First argument is that an electron does not have a substructure in form of other subparticles. And the argument is we have bombarded electrons, for instance, by protons, with sufficient energy, and if there would be a substructure, the electron should have been decomposed. But that is not an argument in this case, because the subparticles do not have any mass and any inertia. So if I bombard such a subparticle, basic particle, by, for instance, high energy proton, then it will be accelerated very, very strongly, but the other subparticle can follow any acceleration because it does not have any mass. That is no problem. And so it is principally, fundamentally impossible to decompose such a particle with bombardment. And then the other thing is, by scattering experiments, it is shown that this particle is very, very small, not extent, but it's very small extension, if any. But what happens there, that is scattering of a subparticle at a proton or at a quark or whatever, and this shows that the scattered particle indeed is very small. But what is small here? That is the electric charge on one of the subparticles, and that is small, maybe 10 to the minus 19, 18th or 19th meter, but the particle itself is much bigger, around 10 to the minus 13 meters, what I will show you. Okay, now the next question. How can it be that such a particle, which is built by massless constituents, can have any mass? Answer is, any extended system has inertia, even if the constituents do not have any mass. This is not an idea or a possibility, but it is completely inevitable. Any extended object must have inertia. The cause is the finiteness of the speed of light, by which the binding forces of the subparticles are bound to each other, are propagate. The binding fields propagate at the speed of light, and that is limited. This is the OIC, that's my statement, the only mechanism for inertia in physics, and it covers all occurrences of inertia in physics, and I will show you how it works. So, first question, how can a system be extended? There are two possibilities in general. The constituents of an object are bound in a way that the distance is kept. That is something we know, for instance, for atoms which are bound to build a molecule. The atoms are bound to each other, but in a way that they do not touch, otherwise the atoms would be always decomposed or whatever happens. The other thing is something we are very familiar with, the planetary system. There's a force in the middle, going to the middle, and the constituents have a mass, but here the constituents do not have any mass, so this second possibility is not possible here. We have only the first possibility, that the subparticles are bound to each other to keep a distance, and that's normally done, and that's not very new in physics. The binding force is a multipole force which has potential minimum at some distance. This blue particle has this blue field to all directions, but I only show this direction. And this has a potential minimum at this place. And here's another particle which resides at this potential minimum. It also has a field, and this field is this one, the more red one, or brown one. And the blue particle is in the potential minimum of this. And so they are bound to each other. If I would press both closer together, they would be repelled of each other, or if I try to pull them apart, they would be drawn back again to be at this equilibrium distance. And this again, to say it again, it's not new. The atoms in a hydrogen molecule are bound in a similar way, to keep a distance but to be bound to each other. Now the point is, of course, if I would touch such a this blue particle and draw it apart, the other particles, the red one, would follow because the distance has to be kept. But this cannot happen instantaneously. There is the limited speed of light between both. It takes some time until the other particle notices this. And this is something, this is a mechanism which causes inertia. And I know that it's sometimes difficult to visualize this process. I've made a little animation to show it how this works. So here we have again the particles in a simplified picture. Now I start to move the blue particle, and there's a little spring which should indicate whether there's a force applied or not. Now we apply a force, draw it to the right. And we have to draw it to the right because we have to take it out of the potential minimum that needs a force. And if this blue particle moves, of course it takes its field with it, but with a delay. First the closed parts are moved, then the second, later the other parts further away are moved. Like you see, they are moved, and now the part where the minimum is moved, and the right particle will immediately follow because it has no mass. It's always in the minimum of this field now. And now, as the red particle moves, also the field of the red particle will move. But first the parts here close to the red particle, later the other parts. And now, after some time, they will speed up. The red field is speeding up, and it will come up, close up to the particle. And now, as the particle is again, the blue particle is again in the potential minimum of the red field, there's no further force needed, and both now move at constant speed to the right. That means to summarize this, to get such a configuration to a different state of motion, we need intermediately a force, and after some time there's no force anymore needed. And that is what we mean when we talk about inertia. We need intermediately a force to get a different state of motion. Was this understandable, or shall I show you the sequence once again? It's good?
Yes.
Okay. Okay. This is again the static picture, and this I've described this shape of a field by this equation. This was the simplest equation which I could find to have such a shape. I've taken the simplest which I could find, yes. And what you find here is F is a force. If you take something here away, like this little symbol shows, S is the field constant of this field. We will later see what this field is. And R0 is the equilibrium distance, and of course the difference causes linearly here the field, and this is the factor which describes the whole behavior of this field. So, now, we have this equation here to strong force, that is later, we'll come back later to it. Now we can make a quantitative calculation, which is not very difficult. We say, okay, here this was our equation, you have seen it, and now I apply a constant, not a constant force, but a constant acceleration to the blue particle. And if I do this, then we know from classical mathematics or physics at school what our equations are. This is the temporal distance between these both particles, if we assume the speed of light, and this is a normal acceleration formula. If you can combine this to see if the particle is permanently, constantly accelerated, what the force will be. It will be a constant force. It follows a simple calculation, and we end up with this equation for the force independence of the acceleration, if we assume this field shape. Now we can see this is a proportionality between the force and the acceleration, and so we fulfill Newton's law of motion. Newton has stated his law of motion without any argument, but here we have the argument, I think the first time in physics, that we have a proportionality between acceleration and force. So we can, following Newton, build the cohesion of both, and then, according to Newton's definition, the inertial mass. Then we can replace the distance of the particle by the radius of the particle, and end up with this equation, which is already quite simple. The mass depends here only on the variable radius or distance. And this is still unknown, that is the field constant. And we will solve this now soon. Again, here's our equation for the mass. And now we take, we have to find the field constant. Now, if we have a charge particle like the electron. We know we have a magnetic moment. The magnetic moment follows this rule, that is a classical rule for the magnetic moment, and we can now combine both equations by, this is only the detection of this, we can combine both equations by eliminating the radius, and we end up with this equation, you see? And do you know this equation? If you are a particle physicist, I think you know it. It is very well known for the electron. It is a Bohr magneton. And that's now very simple. We can use the measurements which have been done with the Bohr magneton and know now what S is. S is this product of h bar and speed of light. And we can now insert this here in this equation and end up with this very, very simple equation for the mass of an elementary particle. And you can show, and we can show that this equation is true for all leptons and also for all quarks, and I think that's quite difficult for photons, but test something else. But we will see that this h bar times speed of light is always said, what does it mean, this Planck constant? How does it come from, and so on? They say it comes from the electric force. That's not true. This product is the field constant of the strong force, and I will show you it. Go right there, yeah. Okay. Now we can build or find the famous relationship between energy and frequency. Here again we have our mass equation. And here we have this relation between mass and energy, which we can deduce also by this model, but I take it here as a fact. Now we can combine these both equations by eliminating the mass. What is the result? The result is this here. And now we can use the geometry of the circuit, the circular motion here again, and insert it by eliminating, combine by eliminating the radius, and what is the end? That is this very famous equation. We know that this equation was found for photons by Max Planck, and we know it's right. It's used in many circumstances, but it was never derived. But with this particle model, we can derive this equation. The first time, I think, in the history of physics. Okay, and strong force again, that we will come to this. We have another thing that is a side effect of relativity. We know that we have contraction if we put some object to motion. And if we put this electron or whatever it is to motion, we will, the radius, the size will contract here by the Lorentz factor. So inevitably the mass will increase by the Lorentz factor. So we have the relativistic increase of mass in a very, very simple way. And we can also consider if we put this object to motion, we have an increase of energy by the kinetic energy, we have an increase of mass, and if we combine both, we end up with this very famous equation of Einstein. If you look how Einstein has used this in a very intelligent but also very complicated way, here it is very simple. It follows from this particle model. So spin is also something we can reorder here, this equation, and we end up here with the classical definition of angular momentum, and we see it as a constant independent of the particle. This result, we will, as long as we can use this equation and we use it for leptons and for quarks, we end up with this constant angular momentum. Now we know that in our practice, here's a factor of 1/2 missing. The reason is that here these subparticles do not have a known mass, which is a classical model. It would be assumed this way, but it's more a dynamical process of fields, as we have seen. That would explain that their mass should be at the end a factor of 1/2. But what we already see here is it is constant. All elementary particles, or fermions, one can say, have the same angular momentum. And it is classically derived with any use of quantum mechanics. We do not need a Hilbert function, we do not need anything else. It comes out here from a simple. So, now mass equation. What is the force? I've spoken about the strong force, and normal understanding is that the electron is only subject to the electric force. We can try it. We take how it works with the electric force. We take here the field constant of the electric force, we know it, insert it here into this equation, and we calculate with this equation the mass of the electron, and the result is this. But the result is wrong, as you know. The true value is this, and this is several hundred, factor of several hundred different, so wrong. But if we insert here the strong force, then we get a very precise result, which is almost 1 to a million. So this is a very good argument that in the electron, that is a strong force which keeps the particles together. So, another thing, physical meaning, in the textbooks they say Planck's constant and fine structure constant. It's a miracle, say many people. They say in textbooks what this means physically. Here it's very clear what it means. We have seen here this factor is the field constant of the strong force, so we can say the Planck constant is strong force divided by speed of light. And now we can see here the definition of the fine structure constant. You know this. This is the electric force, and this is the inverse now of the strong force. So what is the fine structure constant? It is an indication of the relation between the electric force and the strong force. This is an answer. Yeah. Okay. So, the mass of an electron. We have to, you remember our equation for the mass of an elementary particle. Here we have another, that is the line D factor. The line D factor can also be derived by this model. The reason is, I have now made the calculation only assuming that the force in an electron is the strong force, nothing else. But the electron has an electric charge, and this electric charge is distributed half of elementary charge to both subparticles. And if this is taken into account, there is a repelling force, so the electron becomes a little bit bigger. And if you calculate what it is and what it means for the mass or for the magnetic moment, we end up with this Landé factor. I have shown it here, I just tell you that. You know that in the 1940s, Julian Schwinger has found this Landé factor by quantum mechanical means. He has invented virtual particles to explain them, and it was a good result, and he's got the Nobel Prize for it, Nobel Prize for it. But we do not need this complicated way. Here we have, without any Nobel Prize, the same result for the Landé factor. It can be done classically, and I think that is some very fascinating thing. So, when we calculate the mass of the electron by this means, only using our classical model, we come to this result. And if we take the measured value, it is this one, and you see the difference is very small. The difference is a bit worse than 1 to a million. And this is a good indication that this is a working model, not only an idea. Because if you have only an idea which is in some way correct, in some way maybe not, then you would never have such a precise result. I think that's a good indication for it, in favor of it. Okay, now we have for mass two models which are competing. The basic particle model, which I've shown you, and the Higgs mechanism. What is about the Higgs mechanism? The problem is the Higgs field. It's not the Higgs particle which makes the inertia in that theory, but it is the Higgs field. The Higgs field has to have some certain strength so that we have some masses which we observe according to the Higgs theory. And the Higgs theory needs this strength of the field here. That's a consequence of the theory. But what we can see, what we have in the universe, from the cosmological constant is this value. It is not more than this value. If we compare this, we have a discrepancy of 56 orders of magnitude, and also the sign is wrong. So we can say it in simple words, the Higgs field does not exist in the universe. That is proven by cosmology or by astronomy. But still people believe it is not. Oh, right. The other one is better. So this, about the theory a little bit. This is the equation of the Higgs theory for the mass of a particle. Here we have a factor V, which is a general constant in the Higgs theory, given here, And here this is the Yukawa coupling. But the Yukawa coupling does not follow from the theory. The Yukawa coupling is not nowhere given. If I ask a representative of Higgs, what the, for instance, what the Yukawa coupling of the electron is, then he tells me, yes, measure the mass, please measure the mass of the electron, then you can calculate what the Yukawa coupling is. But that is upside down for the theory. The theory is supposed to tell us in advance what the result is. So Higgs theory does not give us any numerical usable value. And this particle model, what I've shown you, has an accuracy of almost 1 per million. That is a big contrast. Okay. So, summary for mass. The cause of inertial mass is that any extended object inevitably has inertia. The basic particle determines the mass of a particle from its size for an accuracy of better than 10 to the minus 6, and further properties of the particle are derived from given classes. This is the only mechanism for inertia needed needed in physics, and it covers all occurrences of inertia in physics. And what does the Higgs model giving us? It's undefined, and the Higgs field does not exist, to say it in simple words. Okay, now, relativity. I said also or announced that this model also explains relativity. Special relativity is given, and this is a Lorentzian version, not handling with space and time. Space and time are inventions of the human brain, good concepts, but not physics in my understanding. Here we have the critical thing. Contraction means a contraction. These are three elements: contraction, dilation, increase of inertial mass, and motion. Okay. Contraction is an old story. It has nothing to do with this model. It's a general property of fields, not electric fields, but Heaviside has found this for electric fields derived from the Maxwell theory. Lorentz has said, okay, then the Morley apparatus contracts in motion by this factor, and so the null result is very clear. And this is now found. It was also accepted as an explanation by Einstein, but it has something like an ether. Einstein didn't want it by what this is by religious reasons, but he was a positivist. So he did not want an ether. But now it is thought that it is shown now that this relation is true for all kinds of fields, which has nothing to do originally with relativity. So next thing is dilation. Dilation comes from the fact that there is a permanent motion of speed of light. One can say speed of light, we learn it's the fastest speed that is possible in physics. It is not the fastest speed in our world, it is the only speed which is in our world. And anything which does not have the speed of light, like all these objects here around, are configuration speed. You can have two particles that are shown which orbit each other with the speed of light, but the whole configuration can be at rest, of course. But the lowest level particle is always moving with the speed of light. And that causes dilation. And you see here that it's the Lorentz factor. The Lorentz factor follows from Pythagoras. Also, this is also true for this particle model. This is orbital motion. Here we have it again. Orbital motion, now in a different view. The subparticles orbiting each other, now at rest, but if the whole thing is moved, for instance, to an axial direction, then from the circuit turns to a helix, and in the helix we have a longer and extended period time, and this is again Pythagoras telling us how much extension is, and we can calculate this with this equation, and it's the Lorentz factor. Again, the Lorentz factor is Pythagoras, can only say it again and again. And this is a deduction of speed of light, of the speed of time in such a configuration. So can also derive these equations which follow the next directly. I do not explain them here, but we need them for general relativity, which also becomes very simple in this way. So mass increase I've already shown you. Mass increase is very simple with this model. Motion. The particle will shrink by the Lorentz factor, so the mass increases by the Lorentz factor, and becomes Einstein's famous equation between energy and mass. So now special relativity is fully explained. All other occurrences or consequences of special relativity follow from these facts. Now we do it with general relativity. In general relativity again, the Lorentzian way, that has nothing to do with space and time, but it's very much more fundamental and physics related. It means Einstein's relativity, to say it again, is based on the strong physics principle. That means the assumption that gravity and acceleration are two words for the same fact. But this statement is falsified. So Einstein's general relativity does not have any logical fundament. Acceleration and gravity can be distinguished. Very simple. If an observer who wants to know whether it's accelerated or in a gravitational field, he can have a charged object like an electron with him. And if he's accelerated, the electron will radiate. But if he's at rest in a gravitational field, there is no radiation. Where should it come from? Energetically. And another thing, dilation occurs in it, so that clocks slow down in a gravitational field, but not at acceleration. For instance, in the near storage ring and so on, and so it was shown that the dilation there is only related to the actual speed of a particle, like a muon or whatever, but in no way to the acceleration, which is very strong in such a muon field. So, Einstein's general relativity has no logical fundament, but Lorentz has no problem with it, or used with Lorentz. The fundament, the general relativity, if we go this way, which I've shown you, has two fundaments. One fundament is radiation of speed of light in the gravitational field. That is effect which we know for sure and have heard many times. And this particle model, which is also needed for this. And both is physics. It's not any abstraction or so. In contrast to Einstein like says space-time and gravity geometry, we do not follow this. And for Einstein, you need Riemannian geometry, which is extremely difficult. You know, a curved four-dimensional space is difficult. We do not need this. What is gravity? Gravity is the change of the speed of light in the vicinity of an object. And this is the equation which describes this. You see, this is the distance here, r, from the center of the gravitational source. This is the theoretical speed of light, and that is the reduced speed of light. If the farther you away, the more closer is this speed of light to this speed of light. If you are closer to an object, speed of light is reduced. We can deduce this. Einstein has deduced this equation. We can do it without any Einstein. Okay. Okay, I have to come to the end because it's getting close and it's half time. I will show you something. The Shapiro experiment, you know it, that was a practical way as this reduction of speed of light was measured. If the sun here, if the beam, here, the radar beam is going close to the sun, the time is expanded, the speed is reduced, the light is reduced. Now we can say, yeah, we have again this confirmed, this equation. Now we can say around the sun or any object, we can think we have a surface of constant speed of light, and on the outer balls, what is it? Yeah, spheres, on the outer spheres, speed of light is higher, here speed of light is lower. What happens if we have some object going through it, like light beam, it is reflected, that is classically reflected. And you can calculate starting from this equation which I've shown you, and the result is for the vortex this, and that is Newton's law of gravity. Here deduced, not believed, like Newton did it, but deduced. And the full deflection is this famous value which made Einstein famous. But here, when we make this reduction, this deflection model, it's exactly the same result like with Einstein. Not only by numbers, but it is also algebraically, by algebra, it is the same result like with Einstein. Einstein has got the Nobel Prize for it, and this was his breakthrough. It was not known, or nobody had at that time had the idea that it is reflection. But it is that simple. So, what is about a particle at rest? This is our basic particle, subparticles orbiting. Now, without a gravitational field. Now, we switch on the gravitational field, and now the path of these particles is reflected. They are accelerated, continuously accelerated towards the gravitational source. There is this path of light which I've shown you from the sun. It's wound up here, and the acceleration I've shown you is this, and we have deduced this, which is Newton's law of gravity. And what we can see also, there is no dependency of mass. Any particle has the same refraction here, So the same, we have the same for any object, the same acceleration in the gravitational field. That is normally called the weak equivalence principle. We do not need an equivalence principle because it is so normal that it cannot happen in a different way. Hello? We have 6 minutes, I think. Yeah, it's indicated here, it's very simple. So, treatment of gravity, something I would like to show you. This looks complicated. These are all the proofs of general relativity as proofs for Einstein theory. In the Lorentzian way, we get the same thing. And one very important thing which explains most of it is the Schwarzschild solution. I think you know the Schwarzschild solution. Schwarzschild, Einstein's equations are very complicated. Schwarzschild has found this, and he has made a reduction of it to a simpler case, to the case of a circular symmetric field like around the sun or in the star and so on. And this is his result, the Schwarzschild solution, the simplified solution. And this can be now deduced very simply from, this is again the equation I've shown you, that relativity, we split this speed into two parts, we need polar coordinates. This is without the gravitational field. Now we switch on the gravitational field, and now we have to replace, speed of light is reduced depending, I've not shown you, but the reduction of speed of light is depending on the direction, and the behavior of fields is so that also fields contract, and if we insert this here, this is quite simple, then we end up with this equation, and this equation is already the Schwarzschild solution. So this is done by Lorentzi, but normally it is given in university lessons in a different way, but with Einstein, of course. And I show you how it is here, that I've copied from a popular textbook about general relativity. Starting from the beginning, simple from the assumptions, yeah, 4 minutes, yeah. And it's more than 80 equations, that is not so bad, but here to do this, we have to handle curved four-dimensional space, Riemannian geometry. And here, Einstein's field equation. If somebody is very intelligent, only few physicists are able to do this, but if somebody is very intelligent and likes to spend a lot of time, he can do this, and he ends up with the Schwarzschild solution. Or you do it this way. You can teach this at school. It is so simple. Everyone can do it. Not only few, what Weinberg has said, less than 10 persons in the world can understand Einstein's general relativity. This can be every person in school who is a little bit intelligent can do this. And the good thing is not that this is, by my understanding, that this is simple, but this is based on physics and not about assumptions about space and time, which I find to be sense. Okay, that's all. I just go to the last ones. And this is a model which shows why the speed of light is in a model, why the speed of light is reduced in the gravitational field. And the interesting thing is that the reduction of speed of light and so of gravity does not depend on the size, and so does not depend on the mass of a particle. It's the same for all particles. This is the equation which you can use here. And it says that strong force is gravity is the side effect of strong force, follows from its moment. We have open problems in cosmology, dark energy problem, the dark matter problem, sorry. We know that the rotation speed is this classically following Newton and Einstein for a galaxy. This is the distance from the center of the galaxy, and that is the possible speed. That is a theory, and that is what we observe when we observe the stars in a if you observe the stars in the galaxy, and this black line is the missing part, and that is called the black matter. If we take this model, then the photons, which with the same contribution according to this model to the degree, build this red curve, and you see it fits very well. We have solved the problem of dark matter. We have also solved the problem of dark energy. Okay, this has to do with inflation. It's not too little time to explain this, but you know what it is. We have observed that, or people have observed that the older galaxies, the older supernovae are too slow, moving too slow, or going away too slow, moving too slow. So it's assumed that the newer ones are accelerated, but this calculation is done using the Doppler effect, and the Doppler effect is the speed of light. We can assume, and this is an alternative to the inflation model, that the speed of light was higher over time and decreases more and more. So if we insert this, then we come to the result that in former times, speed of light was higher and the speed of the binomial in old times was higher. There is no reason, no acceleration, no reason for the assumption of any dark energy or something like that. So that's what I have. Okay. May I stop? I have here a summary, but okay, no. Sorry, something that was not, but we can perhaps read it. It's not a summary for what this is.
We're running out of data on the video, so save questions for Albrecht till tomorrow or lunch. Antoine is going to